Hi, I am Sanjay Patel. In this lecture, we are going to see what happens to the ideals and subrings of a ring under a homomorphism. And for this, we need to recall the definition of image and inverse image of a function. We have studied this thing in analysis also. If f is a function from, say, one set to another set, and if we have A as a subset of X, then we define the image of A under F by this symbol or f of A, and it is nothing but set of all values f of x where x belongs to A. So this set is called image set. So image of A under F. We also know what is the inverse image of a set. For finding inverse image, the set should be in the codomain. So I take B subset of codomain, then we define the inverse image denoted by the symbol F inverse B. It is the set of all those elements in the domain set such that the value of these elements must belong to the given set B. So F inverse B is the set of all those X whose values belong to the given set B. And remember, the image set is always subset of, say, codomain, that is Y in this case, while inverse image is always subset of the domain set. It is very clear that if you have function from one set to another set, say f is a function from x to y, if we take some set A, then its image will be here in the codomain set, that is f of A. If we take some set here, say B, then its inverse image will be a subset of domain set. So this is F inverse B. So image is always subset of codomain, while inverse image is always subset of domain. So we want to see what happens to image or inverse image of a subring or an ideal in a ring. So in this connection, I am going to prove the following theorem. So let us write the statement. Let phi from R plus dot to R dash plus circle dot circle be a homomorphism. Okay. Then prove the following. The first one, if capital S is subring of the ring R, then prove that phi of S is a subring of the ring R dash. Okay. Second result, if we have S dash, if S dash is a subring of R dash, of the codomain ring R dash, then phi inverse of S dash is a subring of the domain ring R. Okay. The third result, it is about ideal. Number 3, if capital I is an ideal in the ring R, then prove that the image of ideal I under the function phi, that is phi of I, is an ideal in the ring phi of R. Now remember, this time it is not the ring R dash, but it is the ring phi of R. Further, about the inverse image. If I dash is an ideal in phi of R, then prove that phi inverse of I is an ideal of the ring R. Phi inverse of I is an ideal of ring R. Okay. So let us prove this one by one. First one is, if S is a subring of R, phi of S is a subring of R dash. Remember, phi is a homomorphism, so it preserves both the operations of the ring. So let us start with the proof. Proof of the first result. We know that phi of S is defined as set of all values phi of x such that x belongs to S. Okay, and we want to prove that this set is a subring. We want to prove that phi of S is a subring of R dash. Okay. For proving this, we must show the conditions of subring. First of all, it should be non-empty. Then whenever, say, x and y belongs to the set phi of S, x minus y also belongs to phi of S, and x into y also belongs to phi of S. So first of all, as phi is a homomorphism, phi of 0 is equal to 0 dash. Okay, we know this thing, and 0 always belong to the subring S, because S is a subring. This S is a subring, so it contains the 0 element, and for the 0 element, the value of the function phi is 0 dash by the properties of homomorphism. So I can say that this 0 dash belongs to phi of S, because it is the value of 0 under phi, and therefore I can say phi of S is a non-empty set. So first of all, you must prove that a given set is non-empty. Next, we take two elements from phi of S. So let say y1 and y2 belongs to phi of S. Therefore, by definition of phi of S, y1 is the value of the function at some point x1, and y2 is also phi of x2 for some x1, x2 belongs to capital S by definition of the image set. Phi of S is set of all phi of x for x belongs to S. So y1 and y2 are values of phi for some x1 and x2. Then I can write y1 minus y2, that is phi of x1 minus phi of x2. But phi is a homomorphism, and we have proved that phi of a minus b is phi of a minus phi of b. So I can write it like this. Okay. And now x1 and x2 are elements of S, and S is subring. That is given to us. S is subring of R. So x1 minus x2 also belongs to R. Sorry, x1 minus x2 belongs to S. Okay. If x1 minus x2 belongs to S, I can say that phi of x1 minus x2 belongs to the image set phi of s. That is, y1 minus y2 belongs to phi of s. See, from where we have started? We have started with y1, y2 belongs to phi of s, and what we have proved is y1 minus y2 also belongs to phi of s. Thus, for every y1 and y2 belongs to the set phi of s implies y1 minus y2 belongs to phi of s, and this is my second result. The third result is about multiplication. So I will be taking the same y1, y2. I will not write again. For the same y1, y2 here, let me show that y1 into y2 also belongs to phi of s. So y1 into y2, y1 into y2, that is dot circle, because y1, y2 are elements of the codomain, and multiplication in codomain is denoted by dot circle. This is equal to phi of x1 dot circle phi of x2, which you can rewrite as phi of x1 into x2, because phi is homomorphism. So this is an important step. This is equal to, say, phi of x, where x I can write as x1 dot x2, but x1 and x2 are elements of s, so x1 into x2 also belongs to s, because s is a subring. And remember that x1, x2 belongs to s, so their multiplication also belongs to s. So what we have proved is y1 dot y2 is of the form phi of x, where x belongs to s, and that means y1 dot y2 belongs to phi of s. So this implies y1 dot y2 belongs to phi of s. So thus, for every y1 and y2 belongs to phi of s implies y1 dot circle y2 also belongs to phi of s. This is our result number 3. So from 1, 2 and 3, it follows that phi of s is a subring. In 1, we have shown that phi of s is non-empty set. In 2, we have proved that whenever y1, y2 belongs to phi of s, y1 minus y2 belongs to phi of s. In 3, we have written that y1 into y2 belongs to phi of s. So from 1, 2 and 3, we have phi of s is a subring of r dash. Phi of s is a subring of r dash. Let us prove the next result. Number 2, we want to prove that, let me write, we are given that s dash is a subring of r dash, and we want to prove that phi inverse of s dash is a subring of r. So inverse image of a subring is always a subring. Okay, to prove this, we must prove that phi inverse of s dash is a non-empty set. It is closed with respect to addition and multiplication. So first of all, we have phi inverse of s dash, meaning is it is set of all those elements in the domain which is R such that phi of x belongs to s dash. This is our definition of inverse image, and you want to show that this is a subring. So first of all, we know that phi of 0 is equal to 0 dash, and that 0 dash belongs to s dash, because S dash is a subring. S dash is a subring. So this implies this 0, this element 0 belongs to phi inverse of S dash. Whenever phi of something belongs to S dash, it means that something belongs to phi inverse of S dash. Okay, by definition of this inverse image. So this is our first observation. Let us take two elements, x1 and x2 belongs to phi inverse of S dash. If x1 and x2 belongs to phi inverse of S dash, then by definition of inverse image, this phi of x1 and phi of x2, they must belong to S dash. Okay, but S dash is a subring, so I can say that phi of x1 minus phi of x2 belongs to S dash, and I can also write phi of x1 dot circle phi of x2 belongs to S dash, because S dash is a subring, so it is closed with respect to addition and multiplication. But what is the meaning of this? This means phi of x1 minus x2 belongs to S dash, and this means phi of x1 dot x2 belongs to S dash. If phi of x1 minus x2 belongs to S dash, then by definition of inverse image, I can say x1 minus x2 belongs to phi inverse of S dash, and at the same time x1 minus x2, x1 dot x2 rather, and x1 dot x2 belongs to phi inverse of S dash. Whenever phi of x1 into x2 belongs to S dash, then x1 dot x2 must be an element of the inverse image set. So what we have proved is this. Therefore, for every x1 and x2 belongs to phi inverse of S dash, we have proved that x1 minus x2 belongs to phi inverse of S dash, and x1 dot x2 belongs to phi inverse of S dash. This is my result number 2. So from 1 and 2, the conclusion is phi inverse of S dash is a subring of the ring R dash. Subring of the domain ring R. The next two results is for ideals. We want to prove that image of an ideal is ideal and inverse image of an ideal is also an ideal. So result number 3, what is given to us is capital I is an ideal in the ring R, and what is to prove in this result is the image of the ideal I, that is phi of I, is also an ideal in the ring phi of R. It is not in R dash, it is in phi of R. That is important here. So first of all, we have phi of I by definition of image set. It is set of all values of the function phi for different x belongs to I. So this is our image of the ideal I, and we wanted to prove that this is an ideal. This phi of I is an ideal. So for ideal, we have to prove two things: that it is a group with respect to the operation of addition, and also it satisfies that special condition of ideal. If one element is in the given set and other element is in the ring R, then that product belongs to the given set in any order. Okay. So Let us begin by proving first thing, that here I is an ideal as capital I is an ideal in R. It is first of all a subring of every ideal is always a subring, but a subring need not be an ideal, and this implies phi of I, okay, phi of I is a subring of R dash. It is a subring of R dash. Okay. So because of that previous result which we have proved, and that means for every say y1 and y2 we take from the set phi of I, implies we have y1 minus y2 belongs to phi of I. That condition is already there. We don't want multiplication, but this thing we can say as our first result. Okay, so this is the first requirement for the ideal. Okay, now to prove that this is an ideal of phi of R, phi of I is an ideal of phi of R, let us take one element from the given set. Let say y belongs to phi of I, and one element I am taking, say R dash, belongs to phi of R. These two are arbitrary. Okay, what I will be proving is y into R dash belongs to phi of R, rather phi of I. Okay, same way R dash into y also belongs to phi of I. Now y belongs to phi of I means y is equal to phi of x for some x belongs to I, and R dash belongs to phi of R as R dash belongs to phi of R. We can say that there is some x belongs to, let me not call it x, use some other notation, that there is some R belongs to R such that phi of R is equal to R dash. Okay, and now let us multiply the two elements y and R dash. If I take y into R dash, therefore y dot R dash is equal to phi of x dot phi of R, which you can write as phi of x into R. Okay, now what is x? X belongs to I, is here, and R belongs to R, and R belongs to capital R. And what is I? I is an ideal. So therefore x into R belongs to I, because I is an ideal. Okay, so if x into R belongs to I can say that phi of x R belongs to its image, that is phi of I. But what is phi of x into R? Phi of x into R is y into R dash. This is R. So that is, I can say y dot R dash belongs to phi of I. Remember, we have taken R dash belongs to phi of R. So what I have proved is this, Thus, for every y belongs to phi of I and for every r dash belongs to phi of r implies y dot r dash belongs to phi of I. And similarly, we can prove that r dash dot circle y belongs to phi of I for every y belongs to phi of I and for every r dash belongs to phi of I. So thus phi of I is an ideal of the ring phi of R. So this proves the result 3. Okay, so if I is an ideal in the ring R, remember that phi of I is an ideal of the ring phi of R. Okay. The last result of this is about inverse image of an ideal. So number 4, what is given to us is, say, I dash is an ideal of the ring phi of R. Okay. What is to prove is phi inverse of I dash is an ideal of the ring R. Let us prove. First of all, note that the meaning of phi inverse of I, that is phi inverse of I dash, is that of all those elements in the domain is R, such that phi of x belongs to I dash. So this is our definition of inverse image set. We want to prove that this set is an ideal. Okay, this set is an ideal. So first of all, we'll prove that it is closed with respect to addition, and then we'll prove the condition for ideal. So note that I dash, or let me write directly. Let us start with two elements. Say x1 and x2 belongs to phi inverse of I dash. That implies phi of x1 and phi of x2 belongs to I dash by definition of inverse image. But what is I dash? I dash is an ideal, so it is a group with respect to operation of addition. So phi of x1 minus phi of x2 also belongs to I dash, because I dash is an ideal of phi of. Okay. So this gives me phi of x1 minus x2 belongs to I dash. But whenever phi of something belongs to I dash, we can say that that element x1 minus x2 belongs to phi inverse of I dash. So what is proved? We have proved that for every x1 comma x2 belongs to phi inverse of I dash, phi inverse of I dash implies x1 minus x2 also belongs to phi inverse of I dash. Now it remains to establish the condition for ideal for the set phi inverse of I dash. So we'll take one element from a ring and one element from the given set. So let x belongs to phi inverse of I dash, Okay, and I'm taking one element from the ring, say R. R belongs to R. Okay. Now, as X belongs to phi inverse of I dash, implies this phi of X belongs to I dash. Okay, phi of X belongs to I dash. That is, let me call it number 1. Also, this R belongs to R implies phi of R belongs to phi of R. That is number 2. But I dash is an ideal, but capital I dash is an ideal. Okay, it is an ideal of the ring phi of R. Yes, I dash is an ideal of the ring phi of R. I dash is an ideal of phi of R. So therefore, I can say from 1 and 2, phi of X dot circle phi of R belongs to I dash, and phi of R into phi of X also belongs to I dash. Okay, and if you simplify this further, what you will get is phi of X into R belongs to I dash, and phi of R into X also belongs to I dash. This also belongs to I dash. Okay, but this means X into R belongs to phi inverse of I dash, and this means R into X belongs to phi inverse of I dash. So what I have proved is, for every R belongs to capital R, and for every R belongs to R, and for every X belongs to phi inverse of I dash, we have proved that X into R belongs to phi inverse of I dash, and R into X also belongs to phi inverse of I dash. So this and result number 1 together says that phi inverse is an ideal. So from 1 and 2, it follows that phi inverse of I dash is an ideal in the ring R. Okay, so this is about image and inverse image of subrings and ideals in a given ring under a homomorphism. So this is something useful, and with this we come to an end of this lecture. And the next lecture we are going to define a very special set associated with homomorphism, and that is very, very important. So till then, goodbye and thank you.